Hey pre-calc class, this is my second attempt at your video for today, so let's hope this one sticks. We're going to continue to work on solving trig equations, and I think I'm going to make a little bit of a challenge video after this if you'd like to push yourself a little bit more. There's a ton of stuff we can do with the solving trig equations, and we didn't get to really do any proving trig identities, so I didn't want to take you too far down this road because it could get pretty tricky. But I will post a few challenge videos if you're feeling like, man, this is a breeze and you want a little bit of a push here. I don't know if anyone's feeling like that, but you know, if you're bored, you don't want to watch Netflix, you can do some trig. Anyway, so today we're going to focus on inverse functions. And we're also going to look at functions with multiple angles, and we'll start with the latter, functions of multiple angles. All the rules that we talked about last time are still going to hold true, so keep that in the back of your mind, all the solving, but we're just going to look at what happens when we add a little bit more to the angle portion. So here's your equation, 2 cosine of 3t. And remember, this 3t, this piece here, is inside of the cosine function. So that's all one part. It's just like if we had an equation 2x minus 1 equals 0, where x is the cosine of 3t, right? So what we're going to do is try and isolate the function, just like we did in the last video. Function. Ooh, spelling, not my strong suit today. And so essentially we're isolating this x, right? So I'm going to add 1 to cosine of 3t is equal to 1. Divide by 2. So the cosine of 3t is equal to 1/2. So I've isolated the trig function. I've done that part. It's a little bit trickier here now because I have 3t inside the function and not just x. So for simplicity purposes, I'm going to think about this piece here as just one variable. So let's say we had the cosine of theta is equal to 1/2. All right, and this is what I want you to solve. Well, let's pull up our handy dandy unit circle and see if we can find where the cosine is equal to 1/2, what angle that occurs at. And hopefully, if you memorized your unit circle, you know this by now, but for those of us who haven't, let's pull this up. All right, so, So cosine, remember, is your x value on the unit circle, so we're looking for where x is equal to 1/2. And I see that here and here. So 5 pi over 3 and pi over 3, all right? So theta then is equal to pi over 3, and theta is equal to 5 pi over 3. And just like last time, we're going to add on 2 pi n to the end of that, right? Because I could go here, that's one value, or I could go all the way around my unit circle and back up to pi over 3, that's another value. Or I could go all the way around to 5 pi over 3, all the way around again, all the way around again and back. And so adding on any increments of 2 pi will still give us the same values. So I'm going to actually get rid of this so I have a little more space here. So remember though that we weren't actually solving for theta. That wasn't my goal. I was solving for 3t. So what I need to do is, instead of saying theta is equal to pi over 3 plus 2 pi n, I should really be saying that 3t is equal to those values, right? So I'm solving for what t is, and that whole angle is equivalent to 3t, right? In this case here, theta is just representing 3t. So if I want to solve for t, if I want to get t alone, well, I'm going to have to divide everything by 3. The 3's would cancel. I get t is equal to, well, pi over 3 divided by 3 over 1. That's the same as pi over 3 times 1/3, which would be pi over 9, right? So when I'm taking a third and dividing by 3 again, I get ninths. So that first piece there simplifies to pi over 9. And then the second piece, it's 2 pi n divided by 3. Well, nothing there can be simplified, so I'm just going to leave it as that. So t is really equal to what we got for theta, the pi over 3 plus 2 pi n, divided by 3, because inside our function was 3t. I'm going to do the same thing for the second angle, 5 pi over 3. And so there, 5 pi over 3 divided by 3 would be 5 pi over 9, 5/9 pi. And 2 pi over 3 doesn't simplify, so I'm going to leave that. And we're adding on 2 pi over 3n, okay? So that's what your actual variable is equal to, whereas the theta, the angle we found, was pi over 3 and 5 pi over 3. All right, so let's try another one in the same fashion. Here we have 3 times the tangent of x over 2 plus 3. Again, remember that this x over 2, that's inside of the function. So I'm going to, just like before, isolate the function. So let's isolate tangent. If it's confusing to you now, right off the bat, we can replace x over 2 with theta. And just remember, theta is really x over 2, right? And that's what we're solving for x. Okay, so I'm going to isolate tangent. So 3 tangent theta is equal to -3 divided by 3. Tangent of theta is equal to -1. Okay, so if I were trying to solve for theta, I want to look on my unit circle and say, where is the tangent equal to -1? Well, remember, tangent is sine over cosine, which on our unit circle, y over x. So which point can I divide the y by the x and get -1? Well, that is going to be here, 7 pi over 4, and here at 3 pi over 4, right? So I want you to think about that. So we can write theta is equal to 3 pi over 4. Theta is equal to 7 pi over 4. When I think about adding on 2 pi n, one thing I do notice is that if I actually took 3 pi over 4 and I added just pi, or 4 pi over 4, I would get 7 pi over 4, right? And that's because these two values here, right? Those are pi spaces. 180 degrees is pi radians. Those are pi radians away from each other. So I could just take this smaller one, add pi n instead of 2 pi n to get 7 pi over 4. I guess I should do it the other way. Oops. We could add pi that way, because that's how our unit circle goes, to get 7 pi over 4, add another pi to get back here, and continue doing that. So instead of me actually having to deal with two angles, I'm just going to deal with this one, 3 pi over 4, and I'm just going to add on pi n to keep it the same. Now if you actually had two angles here and you solved them both and added on 2 pi n, that is perfectly fine. You'll get all the values. Some of them will just be redundant, okay? So usually when you're dealing with tangent, you only have to add on pi n instead of 2 pi n. But let's go back to what our main goal is. So we have figured out theta. We know that that's the angle that solves this equation. But we want the x value, and theta is equal to x over 2. So what I'm going to do here is set this equation equal to, x over 2, and I want to solve for x. Well, in order for me to undo something that's being divided, I would have to multiply both sides by 2. So if I do the left side, I just get x. If I do the right side, I have to distribute it. So we get 6 pi over 4 plus 2 pi n is equal to x. If I reduce 6 pi over 4, it's 3 pi over 2 plus 2 pi n is equal to x. So I solved for the actual variable, not just the angle, okay? So the first few problems I'm going to give you to practice have to deal with multiple angles. And then we're also going to look at some inverse stuff. And there's just one other thing I want to show you. We didn't talk about this a lot last time, but combining like terms. So let's say I gave you the equation a plus the square root of 2 is equal to negative a, right? And I asked you to solve for a. Well, the first thing that we would do is combine like terms from opposite sides, right? So I would subtract a from both sides, and the square root of 2 is equal to negative 2a, and divide by negative 2. So a is equal to the negative square root of 2 over 2, right? Well, this is really the same thing here. If we treat sine of x and negative sine of x like a and negative a, you're just combining like terms. So you can always do that with the same trig function. So what I'm going to do here is, in order for me to combine like terms, I'm going to subtract sine x from both sides. So the square root of 2 is equal to negative 2 sine x. And then between negative 2 and sine x is just multiplication, so I can divide that away. So the sine of x is equal to negative square root of 2 over 2. Now what do we have to do? We have to go find our handy-dandy unit circle. Just reminds me of Blue's Clues every time I say it like that. Our handy-dandy notebook. All right, and oops. Let's move this over here. So when I do that, sine of x is negative square root of 2 over 2. So we're looking for, all right, where does the y value say negative square root of 2 over 2? Looks like here and here. So 5 pi over 4, 7 pi over 4. So x equals 5 pi over 4, and you know the drill, plus 2 pi n. And x equals 7 pi over 4 plus 2 pi n. Okay? Now, I want you to think about this in a little bit of a different light. What if instead I gave you sine of 5x plus the square root of 2 is equal to the negative sine of 5x. Almost the same equation, except for you can see that instead of x, I have made it 5x in both of these, okay? So all you would do differently, the angle is still going to come out to be the same, but this would be a multiple angle situation where instead of saying x equals 5 pi over 4, we would say 5x equals 5 pi over 4 plus 2 pi n, right? And then to solve for x here, we would divide everything by 5. So x would really equal 5 pi over 20 plus 2 pi n over 5, right? And same thing for 7 pi over 4, we would divide everything by 5. That gives us our new answers, okay? So just a couple little tidbits there. So the last idea I want to talk to you about is what happens if we can't use our unit circle, right? We've been really relying on our unit circle for a while now. So here, let's look at something that maybe doesn't fall on the unit circle. So we're still solving, we're still trying to find what's the angle, but in this case, we have cosine x minus 3/5 equals 0. So cosine of x minus 3/5 is equal to 0. Well, the first thing I would do is isolate the function, so add 3/5. So cosine x is equal to 3/5. And 3/5, if you look at your unit circle, where'd that puppy go? I don't see 3/5 other than in a radian, and not even there, right? Yeah, no. I don't see 3/5 anywhere, right? So if we can't use the unit circle, that's where the inverse function comes into play. You might have done this back in geometry. If we want to find the angle, we would have to use the function's inverse. So cosine inverse of cosine x, those functions cancel and just give us x. And then we'd be taking the cosine inverse of 3/5, right? If you go to your calculator, which is somewhere, what we would be doing here is 3/5, so 3 divided by 5. We get 0.6. And then we want to use the second button. On your phone, it will say actually second, I believe, but here you're using the shift. And you see the sine to the -1, cosine to the -1, etc. We want to hit, because it was cosine to the -1. That's cosine inverse. And it says 53.1. Now, if you look up at the top corner, I am in degree mode, so this is a degree answer, 53 degrees. If we wanted radians, hit the radian button and hit equals, and it's 0.9 radians, right? They're not going to give it to you in terms of pi because, it's a calculator, but you can think of pi, or 180 degrees, is 3.14 radians. So 0.9, that's got to be less than 180, and we got 53 degrees as our angle, so that makes some sense there. It's about a third of the way across, okay? So x is equal to, now I sort of forgot what I said, 53.1 degrees. Now you might also see in some of your books, you might see this written as arc cos. That's the exact same thing. So people didn't like this notation of cosine to the -1, because especially when you get into calculus, if you're actually talking about inverse functions or exponents, you don't really know what that means, right? We spend a lot of time saying, well, x to the -1 power is really 1 over x, and that comes into play a lot when we do logarithms and exponentials. But cosine to the -1, that doesn't mean 1 over cosine. It means take the inverse, use the inverse function. So arc cosine is another way to say that. You might have that button on your calculator. It should give you the same answer, okay? So let's see if we can apply this a little bit to a triangle. I actually had to do this not that long ago. My father-in-law is a contractor, and he came to me and asked me to help him figure out what angle should he build this door jamb at so this door will stay perfectly flush when it's, when it's just a little bit open, so that it doesn't swing open anymore or something like that. So anyway, I had to do some of this trig to figure out what's the angle. So I have this right triangle here. We know the 3 sides, but we don't know what this angle is. We know this is 90, but I don't know what that top angle is up there. So I have a bunch of different functions we can set up. We're just going back to your good old friend, so doa. So because we know all 3 sides, it doesn't matter which of these functions you use. We could do sine. So sine uses the opposite and the hypotenuse. So that would look like the sine of theta is equal to 12/13. We could do the cosine of theta. That's adjacent over hypotenuse, so that would be 5/13. Or we could do the tangent of theta, which is opposite over adjacent, so 12/5. When you actually solve for one of these angles, you only have to pick one of these. You don't have to do all 3. They're all going to give you the same answer. And so to actually find the answer, we have to use the inverse. So sine inverse of 12/13, or arc sine of 12/13. Cosine is 5/13, then cosine inverse of 5/13 will give me theta. And tangent inverse, or arc tan, of 12/5 is going to equal theta. So let's pick one of those. I'll do sine inverse this time. So sine inverse of 12/13, Oh, that I always do times. Gives me 0.9, and then I've already hit the shift button here, so I want sine inverse. So 1.2, and this is in radians, or if we wanted degrees, 67.4 degrees, okay? So theta is equal to 67.4 degrees, or 1.17 radians. Now, just to confirm, let's say we wanted to do it with tangent. So tangent inverse of 12/5. Second button's already hit. Let's hit tangent inverse 67.4. Same angle, right? Doesn't matter which one you pick because it's all in the same triangle. All those ratios give you the same value. And then if we really wanted to find this third angle, well, all the angles in a triangle add to 180 degrees. So we could use that idea, all right? So why don't you guys go ahead and try the practice I gave you for today. And then again, there's a couple questions